Welcome to the presentation of our paper Robot Learning with Crash Constraints, a work in collaboration with Dominic Baumann, Majid Kadif, Philip Hennig, Ludovic Righetti, and Sebastian Trimpe. So when running learning algorithms on complex systems, it is common to encounter the case in which failed experiments prevent us from measuring appropriate reward values. And this poses a problem when we want to design effective reward functions for learning. For example, when learning parameters of complex simulators of vehicle collisions, the simulator may not converge for some of the parameter configurations. And if it doesn't converge, we obtain no valid reward signal. When learning parameters of machine learning algorithms, we may also encounter situations in which certain parameterizations fail to return a valid outcome. For example, when learning parameters of Hamiltonian Monte Carlo, it is possible that the integration diverges for large values of the step size. Also, when learning the number of layers of a neural network, large numbers could make our machine run out of memory. When learning with real robots, we find also many cases where failures return useless data. In some recent work, failures are explicitly considered, but the data obtained upon failure is usually corrupted or difficult to handle. And because of this data is discarded and the robot is penalized using some heuristic cost values. But designing such heuristic cost penalties requires proper tuning and expert knowledge about the platform. In other cases, failures and successes are not treated separately, but rather part of the same cost function, which results in a cost function with high variance. So in summary, a common issue to all these cases is that failures are not treated using well-founded methodologies, but rather by handcrafting user-defined penalties. And in general, this requires expert knowledge to properly design a valid cost function. But such expert knowledge may not always be available. In recent work, failures are modeled as binary constraint violations, but the method proposed by the authors only expands locally around the safe region. And we would like a method that can also explore outside the initially given safe region. So our first contribution is a framework that treats failures in a principled manner. And for these, failures are interpreted as constraint violations rather than cost penalties. In particular, we tackle the case in which no data is obtained upon failure. So following the naming convention in the literature, we call these learning scenarios learning with crash constraints. And we address the controller tuning problem using Bayesian optimization with constraints where areas with failures are avoided as these areas are revealed during learning. We also propose a novel Gaussian process model for the constraint that combines discrete labels to indicate failure and success with continuous observations which are only obtained in the case of success. And in addition, the constraint threshold turns out to be a hyperparameter of our model which can be learned from data. And this mitigates even more the required expert knowledge. So for the first time, to the best of our knowledge, we tackle the problem of learning with crash constraints on a real robot using a principled method instead of heuristic approaches. So the context here is a non-safety critical scenarios where failing is undesired but not catastrophic. We could think, for example, about the first-time design and tuning of controller parameters on a real robot. So contrary to scenarios where failures must be avoided at all costs, our method leverages failures in its favor in exchange of a faster and less conservative learning. We propose a controller tuning problem where the optimal parameters minimize a cost function that encodes the system performance. We seek the optimal parameters inside a feasible region, XS, which is defined as the parts of the parameter space where all the constraints are satisfied. We address this problem using Bayesian optimization with unknown constraints, where the cost and constraints are considered black box functions that can only be revealed through experiments. So the cost here is modeled using Gaussian processes, and the constraint is modeled using GPCR, which is the novel Gaussian process model that we are proposing in this work. So we're going to illustrate how GPCR works with this simple toy example. So the GPCR model that models the constraint behaves as any other Gaussian process around the successful points. But around the failures, GPCR uses variational inference to compute the posterior over the failure locations, where actually no real observation was ever acquired. And as a result, the model pushes up the probability mass above the constraint threshold. So in this way, visiting failure areas is completely discouraged during the search. The acquisition function that we use is expected improvement with constraints, which in a nutshell multiplies the expected improvement criterion with a chance constraint that indicates the probability of satisfying the constraint. We formulate a likelihood function that encodes the no data case by combining discrete labels and real valued observations. So if the experiment is successful, then the constraint observation is modeled as the latent value plus noise and a discrete label equal to +1. And if the experiment fails, then we assume that no measurement was obtained and we inform the model about this with a label equal to 0. In order to formulate such likelihood function, we need to express it probabilistically. So if X is a failure, all we know about the unmeasured observation is that it should violate the constraint, and therefore it should lie above the threshold. And that is encoded with the Heaviside function that we see in the screen. However, we never specify what the value of the observation is. On the contrary, if X is successful, then all the probability mass falls below the threshold C for consistency, as shown by the corresponding Heaviside function. And in addition, we also include a Gaussian that is encoding the noisy observation as part of the model. So for one data point, the likelihood can be written in this compact form, and for n data points, we have a product of Gaussians and Heaviside functions. So such likelihood, when multiplied by a Gaussian prior, induces the following non-Gaussian posterior. So in 2 dimensions, it can be interpreted as a truncated multivariate Gaussian, where the support is restricted to an unbounded rectangle with a single corner. So this type of posterior is intractable, but we can well approximate it using variational inference. And for this, we do moment matching on the 0, 1st, and 2nd order moments using expectation propagation. So the resulting posterior distribution, Q of G, is a multivariate normal distribution. And because such posterior allows to compute multivariate Gaussian predictions, we obtain the Gaussian process that we were looking for. So now, because this model combines notions of classification, but reinterpreted in the regressor, we call it Gaussian process for classified regression, GPCR. And the chance constraint that we mentioned before at location X can easily be computed as the cumulative density function of a univariate Gaussian. So far we have assumed that the constraint threshold C is given. However, such threshold might not always be known a priori. For example, in the carpal system, the maximum deviation from the equilibrium point after which safety cannot be recovered could be unknown. And estimating it could require expert knowledge about the platform, like for example, a good model of the robot and previous interaction with it. So in this work, we assume directly that the constraint threshold is unknown, and we treat it as a hyperparameter and estimate it from data. And for that, we follow a fully Bayesian approach where both the model parameters and the threshold are estimated using maximum a posteriori and expectation propagation. And to this end, the prior over the threshold is chosen as a gamma distribution that places all the probability mass above the highest constraint value observed so far. We illustrate the proposed framework on a quadruped that learns to jump as high as possible. The target is to learn the P and D gains of the joints. And the cost here is formulated as minus the maximum height reached during the jump, which is measured using a motion capture system. So during learning, some parameterizations can cause a failure, as we see in the video. And importantly, the failure is caused because there is a peak in the sum of current that is feeding the motors, and this causes the robot to enter in safe mode. So all the motors will shut down in the middle of the air and the robot lands improperly, crashing on the floor. So essentially, the higher is the sum of currents, the closer we are to a failure. So in this platform, a failure has several important consequences. First, the sum of currents cannot be measured. And second, the motors stop in the middle of the air, so the height measurement is corrupted. So in summary, we just obtain no valid data after we observe a failure. And we are going to model the constraint as the maximum sum of currents observed throughout an experiment. We know that the sum of currents must be smaller than some value for the constraint to be satisfied. However, such value, which is in the slide C, such value is unknown a priori. We use Bayesian optimization with constraints to tackle this problem, where the constraint threshold is estimated from data during the search. So we start with an initial controller that has poor performance, and then we run our framework to search a parameterization that improves such controller. After some iterations, we will encounter our first failure, and the GPCR model is informed about this failure with a discrete label because no data was obtained. And as the search continues, the algorithm tries to avoid failure areas as they are revealed during the search. We compare the controller that our method finds with a good controller found by an expert with manual tuning, as we can see in the middle. While it took the expert significant time and effort to find this suitable controller, our method finds a better controller on a single learning run within 50 iterations. We also compare our method in numerical benchmarks against heuristic strategies that are often used in robot learning papers. These heuristics use user-defined penalties to represent these failure cases. So in general, our method achieves lower regret in all cases in 2, 6, and 10-dimensional benchmarks. It also estimates the constraint threshold with a small error. And in the same way, it finds a higher number of safe evaluations than alternative heuristics. In addition, we compare against popular methods of Bayesian optimization with constraints that seek to avoid failures. Such methods collect a higher number of safe points than our method, but their exploration is quite conservative, which discourages them from leaving the initial safe area. And because of that, they achieve higher regret than our method on average. So in summary, our method achieves the best trade-off between safety and performance. To conclude, we have proposed a framework to address the problem of learning with cross constraints in the context of controller parameter tuning. We have shown that this is useful in robot learning, where the data obtained in failure cases is often unmanageable. We also have demonstrated the effectiveness of our method on a real jumping quadruped, where the best jump improves by about 34% the one obtained with manual tuning by an expert. And we also have validated our method against commonly used heuristics in numerical benchmarks up to 10 dimensions, where our method achieves the best trade-off between safety and performance. And finally, our GPCR model learns the constraint threshold that is unknown a priori, which mitigates the need of expert knowledge even more. So take a look at our code if you want, which is available in GitHub.